The final act of Betelgeuse, a cosmic spectacle unveiled by the James Webb Space Telescope. For centuries, astronomers have gazed at Betelgeuse, the fiery red supergiant in Orion's shoulder, its pulsating glow a beacon of mystery in the night sky. Known as one of the brightest stars visible from Earth, Betelgeuse has long captivated scientists and stargazers alike with its enigmatic behavior. A star over 700 times the diameter of our Sun and roughly 20 times its mass, Betelgeuse has been teetering on the edge of cosmic collapse for decades, its cycles of brightening and dimming hinting at an explosive end. Yet, the precise moment of its demise remained elusive until now. The James Webb Space Telescope, JWST, with its unparalleled infrared vision, has captured a once-in-a-lifetime event. The real-time transformation of Betelgeuse as it begins its cataclysmic supernova phase. This is not just a stellar observation. It is a historic milestone, the closest supernova ever recorded by humanity, offering a front-row seat to the raw mechanics of stellar death and cosmic rebirth. A star on the brink, located just 642 light-years from Earth, Betelgeuse is a cosmic neighbor by galactic standards, making its impending supernova a rare opportunity to study stellar evolution up close. Unlike distant supernovae in far-off galaxies, Betelgeuse's proximity promises a spectacle that could rival the full moon's brightness, potentially visible even in daylight. For decades, astronomers have monitored its erratic behavior, noting its pulsations and irregular dimming as signs of instability. In 2019, a dramatic dimming event, when Betelgeuse faded to an unprecedented low, sparked global speculation. Was this the precursor to its long-awaited explosion? The event, later attributed to a massive dust cloud ejected by the star, only deepened the mystery. Scientists knew Betelgeuse was nearing the end of its life, but the exact timing and nature of its collapse remained uncertain. Enter the James Webb Space Telescope, launched in December 2021. With its advanced infrared instruments capable of peering through cosmic dust and gas to reveal hidden stellar processes. Since its deployment, JWST has turned its gaze toward Betelgeuse, monitoring the star with precision no previous telescope could match. What is revealed is nothing short of astonishing. Betelgeuse is not merely dying. It is undergoing a violent and chaotic transformation, unraveling in real time before our eyes. Witnessing a star's collapse. For months, JWST has been collecting data on Betelgeuse, its infrared sensors capturing details invisible to optical telescopes. The telescope's observations have unveiled a star in the throes of collapse, marked by massive energy emissions, shifting convection patterns, and magnetic fields spiraling into chaos. Gigantic convective cells, bubbles of plasma the size of Jupiter, are erupting across Betelgeuse's surface, hurling hot gas into space at unimaginable speeds. Hidden within the star's light spectrum is the unmistakable signature of a shock wave rippling through its outer layers, a clear indicator that the star's core is beginning to implode. For the first time in history, astronomers are not merely theorizing about a supernova. They are witnessing its physics unfold in real time. This is no simulation or distant observation. JWST is providing a front-row seat to a cosmic autopsy, documenting the moment-by-moment destruction of a star just 642 light-years away. The data is staggering. Betelgeuse's surface is roiling with turbulent activity, its outer shell fracturing under the strain of its collapsing core. The star's magnetic fields, once structured, are now unraveling, creating voids in the plasma and triggering unpredictable outbursts. These observations are rewriting our understanding of stellar death, offering unprecedented insight into the processes that govern a star's final moments. A cosmic crucible. Betelgeuse's supernova is more than a dramatic light show. It is a crucible for the creation of the universe's building blocks. As the star collapses, its core reaches temperatures and pressures so extreme that new elements are forged: carbon, oxygen, iron, and even rarer elements like technetium and yttrium. These are the raw materials of planets, ecosystems, and life itself. Without supernovae, there would be no rocky worlds, no oceans, no living beings. In its death throes, Betelgeuse is revealing the very processes that shaped our own existence, offering a glimpse into the cosmic cycle of creation and destruction. JWST's ability to analyze the chemical composition of Betelgeuse's ejected material has provided a wealth of new data. By studying the ratios of elements in the star's expanding debris, scientists can trace the journey of matter across the galaxy, from the hearts of dying stars to the dust clouds that form new worlds. This is not just a story of Betelgeuse's end. It is a story of our cosmic origins, written in the light of a dying star. The telescope's observations are helping astronomers construct detailed models of the star's final evolutionary stages, potentially allowing them to predict the behavior of other massive stars long before they explode. A multifaceted breakthrough. The significance of Betelgeuse's collapse extends beyond chemistry and stellar evolution. JWST has detected high-energy particles racing outward from the star, heating surrounding gas clouds and reshaping its dusty halo. These shock waves are rippling through the interstellar medium, altering the cosmic environment for light years around. Even more tantalizing is the possibility that Betelgeuse's core collapse has generated gravitational waves, subtle ripples in space-time that scientists have only recently begun to detect. If confirmed, this would mark the first time a visible supernova has been directly linked to gravitational wave data, a breakthrough that could transform our understanding of how light matter and gravity interact on a cosmic scale. The data also hints at an uneven collapse, with magnetic field disturbances and plasma voids suggesting a chaotic end. Some astrophysicists speculate that Betelgeuse's demise could produce a transitional object, neither a neutron star nor a black hole, but something in between. Such an entity has been theorized but never observed, and if JWST's observations confirm its existence, it could represent a new class of stellar remnants. This discovery would challenge existing models of stellar evolution and open new avenues of research into the fate of massive stars. Are we in danger? Given Betelgeuse's proximity, a natural question arises. Could its explosion pose a threat to Earth? The answer, reassuringly, is no. At 642 light-years, we are far beyond the reach of the supernova's harmful radiation. Gamma rays and electromagnetic waves will dissipate long before they reach our planet. However, the explosion's effects on the surrounding cosmos are profound. The blast will reshape nearby star systems, alter interstellar dust clouds, and potentially affect how light travels through space to our telescopes. JWST is actively monitoring the speed and behavior of this radiation front, providing data that could change how we observe the universe itself. The supernova's impact on our galactic neighborhood underscores its broader significance. By studying Betelgeuse's explosion, scientists can better understand how supernovae influence galaxy formation, trigger starbirth, and distribute heavy elements across the cosmos. This event is not just a singular spectacle. It is a key to unlocking the mechanics of the universe's evolution, a mirror of impermanence. Betelgeuse's collapse is a stark reminder of the impermanence of even the most luminous objects in the cosmos. This colossal, ancient star, once a symbol of endurance in the night sky, is meeting its end, just as our own sun will one day fade. Yet, in its destruction, Betelgeuse is not annihilated. It is transformed. Its remnants will seed the cosmos with the material for new stars, planets, and perhaps life. This is cosmic regeneration, a cycle of death and rebirth that has shaped the universe for billions of years. JWST's observations of Betelgeuse are more than a scientific triumph. They are a moment of profound reflection. In the star's fading light, we see our own cosmic roots and a glimpse of what lies ahead. The telescope has captured not just a supernova, but a narrative of creation, destruction, and renewal. As Betelgeuse's light fades from Orion's shoulder, it leaves behind an expanding cloud of gas and debris, a legacy of knowledge, and a reminder that even in endings, there are beginnings. The legacy of Betelgeuse. The James Webb Space Telescope has done more than document a star's death. It has translated the chemical language of life's origins. By capturing the precise moment of Betelgeuse's collapse, JWST has answered questions humanity has pondered for millennia. Where do the elements come from? How do stars end? What awaits our own sun? In the star's final flare, we have glimpsed the truth of our cosmic existence, not as myth or metaphor, but as scientific reality. As Betelgeuse's light fades, it leaves us with a challenge: to continue exploring the universe's mysteries and to prepare for the revelations yet to come. The supernova is not the end of the story. It is a call to look deeper, to ask what else the cosmos is preparing to unveil. With JWST's cutting-edge tools, humanity is better equipped than ever to answer that call. In the silence of deep space, 642 light-years away, a star's life ended in a blinding, thunderous roar. Thanks to the James Webb Space Telescope, we didn't just witness it, we understood it. And in that understanding, we found a piece of ourselves. A cosmic legacy unfolds. The James Webb Space Telescope's JWST observations of Betelgeuse's supernova are not a singular moment, but the beginning of a new chapter in our exploration of the cosmos. As the star's collapse continues to unfold, its implications ripple far beyond the Orion constellation, reshaping our understanding of stellar evolution, galactic dynamics, and the very origins of the universe. The wealth of data pouring in from JWST is painting a vivid picture of a star in its final act, but is also raising new questions. Questions that challenge our assumptions and push the boundaries of what we believe is possible. Peering into the heart of destruction, JWST's infrared instruments have given astronomers an unprecedented view of Betelgeuse's inner workings. As the star's core collapses, it triggers a cascade of events that are both violent and intricate. The telescope has captured the rapid expansion of Betelgeuse's outer layers, driven by shock waves that tear through the star's atmosphere. These shock waves are not uniform. They are punctuated by bursts of energy that vary in intensity, suggesting an asymmetrical collapse. This asymmetry is critical, as it could determine the nature of the remnant left behind, whether a neutron star, a black hole, or something entirely new. The convective cells erupting on Betelgeuse's surface, some larger than entire star systems, are a testament to the star's chaotic state. These massive bubbles of plasma, heated to millions of degrees, are propelled outward by the immense pressures building within the star. JWST spectrographic analysis has revealed the chemical signatures of these eruptions, showing a complex mix of elements being forged and expelled. Beyond the expected heavy elements like carbon, oxygen, and iron, the telescope has detected traces of rare isotopes, such as technetium-99 and yttrium-88, which form only under the extreme conditions of a supernova. These findings are a gold mine for astrophysicists, offering clues to the nuclear reactions that power stellar explosions and create the building blocks of the cosmos. Gravitational waves and cosmic ripples. One of the most tantalizing discoveries from JWST's observations is a potential detection of gravitational waves emanating from Betelgeuse's collapse. These ripples in space-time, first directly observed in 2015 by the LIGO collaboration, are produced by cataclysmic events like black hole mergers or core collapse supernovae. While ground-based detectors like LIGO are sensitive to high-frequency gravitational waves, a supernova like Betelgeuse's could produce lower-frequency waves that are harder to detect. However, JWST's precise measurements of the star's implosion dynamics, combined with data from other observatories, may provide indirect evidence of these waves. If confirmed, this would be a historic milestone, linking a visible supernova to gravitational wave signals for the first time. The implications of this discovery will be profound. Gravitational waves offer a unique window into the universe, carrying information about events that are invisible to light-based telescopes. By correlating JWST's optical and infrared data with potential gravitational wave signals, scientists could gain a more complete picture of Betelgeuse's collapse, from the initial implosion of its core to the shock waves that ripple outward. This multi-messenger approach, combining light, matter, and gravitational data, could revolutionize our understanding of how massive stars die and how their remnants shape the cosmos. A new class of stellar remnants? As Betelgeuse's core collapses, astronomers are eagerly awaiting the answer to one of astronomy's great mysteries. What will remain? The standard models of stellar evolution predict that a star of Betelgeuse's mass, roughly 20 times that of the Sun, will either form a neutron star, a dense object composed almost entirely of neutrons, or a black hole, where gravity is so intense that not even light can escape. However, JWST's data suggests that Betelgeuse's may not fit neatly into these categories. The telescope has observed unusual patterns in the star's collapse, including magnetic field disturbances and voids in the plasma that hint at a fallback scenario. In this scenario, material initially ejected by the supernova, is pulled back toward the core by its immense gravity, potentially altering the outcome of the collapse. Some astrophysicists speculate that this could lead to the formation of a transitional object, something between a neutron star and a black hole, such as a quark star or a magnetar with exotic properties. These objects have been theorized but never directly observed, and Betelgeuse's proximity makes it an ideal candidate for detecting such a remnant. If JWST confirms the existence of a transitional object, it would challenge existing theories of stellar evolution and open new questions about the physics of extreme gravity. The telescope's ability to monitor Betelgeuse's remnant in the years following the supernova will be crucial